So hello and welcome back to this online machine learning course. So in the last video we talked about linear regression. We talked about the mean squared error over here. We talked about how our predicted y would be expressed as a linear combination of all my feature inputs x's and how we could actually draw a best fit curve to actually fit my assumption, to fit my predictions. Now our objective now is to actually learn these b1s, b2s till bn, as well as this b0. Now the goal is to actually feed my machine all the x's, x1 to xn, and somehow predict a y which is as close as the actual y, and thus find out the b1, b2 up to bn and the b0 as well. Now there's reason why I have circled the b1 to bn in green while they are b0 in blue, because we refer these terms, we refer these b1s to bn as weights, while this one is known as bias. This one is known as bias, while this one is known as weights. Now the weights and the biases go hand in hand, and we would be representing our weights as W and our bias as B. Because in the forthcoming slide we would be seeing something in W's and B's only. And as you know, our objective is to minimize the error, right? As we discussed in the last topic. So let's move on. So the rule is actually W. As you can see, the weights and the biases have been denoted in the form I discussed in the previous slide. Weights with W and the biases with B. The weights with W and the biases with B. Now the rule is, for every tth interval or the tth change, okay, so let me change it first. So weight is equal to weight minus eta times the gradient of what your weight was. So this is the new weight after you actually change your weight. This was the old weight, and this is also your old weight, right? So basically the gradient is actually this mathematical operator. It is actually the partial differentiation of the loss function. This is actually also known as the loss function, this mean squared error, because this loss function is actually telling you how much loss or how much ahead are you actually from the real prediction. This error function or the loss function, we can also call it the error function or the loss function. Both go hand in hand. So this is my error function, the mean squared error loss. And so actually I'm doing a partial derivative of each W t, of each W and B, and thus calculating my gradient over here as in the formula above. So yeah, this is actually derived using Taylor series and other various mathematical adjustments, and the algorithm is actually known as gradient descent. So we are discussing gradient descent today in this video. So now the mathematical understanding was maybe quite complicated. So let's get a graphical intuition. So now, for example, consider this. You see the mean squared error loss. Okay. So now let's look at the graph over here. And for example, considering I treat my y as my predicted y as some value of m and x, right? And for different values of m and x, I get a different curve. And this graph which you're seeing over here is a plot between the green would be, okay, let me change the color. Yeah, so the green would be and this axis would be, this is your error axis, and this is which is given by this mean squared error loss, and this is the m axis, right? This is the m axis. I mean, for different values of m, you would be having different values of error, because in place of this yi, you would be placing m x I, right? And so for different values of m, you would be having different errors. So suppose this is my current function, right? This is my current error function. And seldom in machine learning cases, we actually encounter this curve, also known as bell curve in machine learning literature. So for example, let me take an m over here. Okay, let me change the color a bit. Yeah. So let me take an m over here. So on the graph, this point would be somewhere over here. Now our goal is to minimize this error, or this mean squared error, right? So somehow we need to find out the m over here in this point of y-axis, right? The minimum value. We need to find out this m. Now, how do we find out this m? We must be descending down along this slope. The basic intuition is to descend down along this slope. So what would you be actually doing this? You would be taking an m, you would be subtracting the slope, perhaps the slope of this curve. So the slope is actually the error curve surface. So error dE by dm, right? So if your dE by dm, and for example you multiply it with some constant also known as eta, right? And if you do this, so here this quantity, if for example I take my m at this point, this quantity is actually negative, right? So this entire quantity is positive, and which is actually greater than m. I hope you got the intuition. So this m would actually move further, right? To this point perhaps. This would be the new m. This was the old m, and this would be the new m. So similarly, we can further update until we reach this curve. Now the question arises, since we're subtracting here, what would be in this case, right? So in this case, the m would be ahead, and if this is the new m, for instance, like m3, now when I do a gradient descent, my slope would be this, and since the slope is minus eta, this is a negative quantity, and so a negative quantity when this is a positive quantity, and so a positive quantity when is subtracted from m, your graph would be getting back, and so ultimately we are converging towards the minimum m. And that is what my basic intuition is. So for example, initially you might be having this curve, then you might be having this curve, then after few iterations you might be having this curve, then finally you may have arrived on this curve, then you arrive on this curve, and then finally perhaps you arrive on the right curve, which is this curve. So as you can see, from this point we are moving in this direction, and when we are in this curve, this side, we are moving in this direction. Ultimately we are reaching the axis, or the correct line, or the correct values of m. Now, as you can see, it is graphically being represented of how we are actually, what the intuition is, whether JW is actually the cost function or the error function, and W is my weight. Now, as you can see out here, that this is for only when you have a single M, right? Now you can extend this for mx plus c as well. Consider, as in this, for this case, consider for in this case where this could be the error graph, this could be the error graph, this could be the C part, and this could be the M part, right? And so you need to find the set of M and C such that the error is minimized, and which would be perhaps this point where the error is seems to be minimized. And this is how we do by gradient descent. We perform partial differentiation and then we proceed on. And for bigger dimensional, like for these vectors, like if we've got n vectors as such, we cannot see them graphically. Then we look at hyperplanes, and of course we do not look at hyperplanes, but we could look at hyperplanes. We actually tend to the mathematical definition, which is actually indeed this one. We get to the gradient definition, and the gradient definition is actually helps us to extend to multiple dimensions, to multiple matrices, and that is what our goal is. So that is how we actually learn the parameters of M and C and for other vectors as well. So thank you for watching.